Hello my friends and welcome back to the You Can Do TV channel. Hope Cement Works operates as a highly engineered, large-scale cement manufacturing facility, integrating quarrying, thermal processing, and precision material control into a continuous industrial workflow. Commissioned in 1929, the plant remains one of the most technically advanced cement production sites in the United Kingdom, with an annual output of up to 1.2 million tons. Production starts in the limestone and shale quarries, where controlled blasting releases approximately 20,000 tons of raw material per blast. Heavy-duty excavators and dump trucks transport the rock to a three-stage crushing system, reducing material size from over 1 meter to below 20 millimeters. Conveyors then deliver the crushed material to the plant's stone storage facilities. Inside the works, limestone, shale, and supplementary materials such as pulverized fuel ash are proportioned and ground in ball mills containing over 200 tons of steel grinding media. This process produces a fine, raw meal, which is homogenized in blending silos before entering the preheater tower. Within seconds, cyclone heat exchange raises the material temperature from roughly 80 degrees Celsius to over 830 degrees Celsius, preparing it for clinker formation. The heart of the process lies in the rotary kilns. Each kiln measures 70 meters in length and operates at temperatures exceeding 450 degrees Celsius. Here, precise chemical reactions transform the raw meal into cement clinker. Load-sensed drives, refractory linings, and continuous process monitoring ensure thermal stability and product consistency. Alternative fuels, including processed waste and scrap tires, now account for approximately 35% of total energy input, reducing environmental impact. Clinker is rapidly cooled, stored, and later ground in cement mills with gypsum to regulate setting characteristics. Throughout production, automated sampling and laboratory testing maintain strict quality control. Finished cement is distributed primarily by rail, minimizing road transport and supporting efficient, large-scale delivery to infrastructure and construction projects nationwide. The Petersburg Tunnel in Germany forms a critical section of the busy railway line between Koblenz and Perl, where the route crosses the Moselle River near the community of Neef. Under current railway regulations, double-track lines must maintain a minimum track axis distance of 4 meters. The existing Petersburg Tunnel no longer met this requirement, making tunnel enlargement unavoidable. However, due to the strategic importance and heavy traffic volume of this corridor, closing the line was not a viable option. As a result, the project was executed using the tunnel-in-tunnel method, allowing rail operations to continue throughout the 2-year construction period. A dedicated installation site and access road were constructed at the southern portal of the tunnel. Special care was taken to avoid disrupting a nearby camping ground, as tourism along the Moselle River is a key economic factor in the region. The site accommodated offices, staff facilities, workshops, magazines, stockyards, and temporary storage for excavated rock. An earth embankment was formed and asphalted to support heavy equipment and technical installations. During a 4-week planned tunnel closure, the only major interruption to rail traffic, the double-track line was temporarily reduced to a single track to allow installation of essential systems. To ensure maximum safety for both railway operations and construction personnel, a 470-meter-long protective tunnel made of steel and timber was erected inside the existing tunnel. This internal protection structure allowed trains to pass every 8 minutes during construction. Pre-cut works followed, including rockfall protection and slope reinforcement at the portals, ensuring stable conditions throughout the enlargement process. At the southern portal, the tunnel enlargement system developed by Marty Technic was installed. This complex platform integrated all equipment required for excavation, lining, logistics, and worker access. After full assembly and testing, the entire system was positioned inside the tunnel using a large capacity crane. Excavation then proceeded in a cyclic drill and blast process. Drill rigs bored blast holes into the rock, explosives were carefully placed, and blasting was carried out only after track closure and clearance by the railway safety officer. Following each blast, loose rock was removed using hydraulic hammers, and excavated material was transported to the installation site for temporary storage before off-site disposal. Immediately afterward, the tunnel arch was stabilized with sprayed concrete, Shotcrete. Reinforcement steel meshes were installed and supported by lattice girders, then anchored to the rock using up to 5-meter-long rock bolts. A second layer of reinforcement and sprayed concrete completed each cycle, ensuring progressive stabilization of the enlarged profile. Once excavation reached the northern portal, the enlargement system was moved back toward the south. During this return phase, abutments were constructed at the base of the tunnel arch to support the future inner concrete lining. In parallel, additional equipment, including formwork, reinforcement, transport, and ceiling carriages, was assembled at the installation site. This marked the completion of the first major construction stage. To avoid disrupting rail services, the enlargement system was replaced overnight by the pre-assembled formwork carriage. The final inner lining works began at the northern portal. Reinforcement components were transported into position, where workers manually assembled steel arches and meshes under demanding conditions. Despite the confined space, installation accuracy remained within centimeter tolerances. The formwork carriage was then precisely aligned and hydraulically sealed against the tunnel arch. Concrete placement required strict symmetry on both sides to prevent formwork displacement under high pressure. Inspection openings allowed continuous monitoring of concrete flow and compaction. Curing systems prevented rapid moisture or heat loss, minimizing crack formation. Portal structures at both ends were completed using the cut and cover method under extremely tight spatial constraints. After completion of the inner lining and portal works, the internal protective tunnel and installation site were dismantled. With construction complete, the Petersburg tunnel was successfully reopened for full double-track operation meeting modern safety standards while maintaining uninterrupted rail service throughout the project. Underground shotcreting in coal mines represents a significant advancement in modern ground support systems, combining materials engineering, mechanized application, and strict safety control. CNC Civil and Mining Construction has introduced a methodology based on wet, fiber-reinforced shotcrete, commonly referred to as Fibercrete, specifically engineered for underground coal strata. Unlike conventional hard rock shotcrete, this system is designed to compress and confine coal, forming a pressure membrane that works with the geological structure rather than standing rigidly against it. Successful application depends on three core technical criteria. Quality control is essential to ensure raw materials are correctly selected, proportioned, and mixed to produce a consistent wet fibercrete capable of penetrating coal cleats without segregation. Fit-for-purpose equipment is required to pump and apply the material at controlled velocities, ensuring strong adhesion, deep infiltration into the strata, and effective compression of the applied liner. Equally critical are trained operators who understand spraying techniques, material behavior, equipment operation, and site-specific ground conditions, including correct spray direction aligned with coal cleat orientation to enhance confinement. The Fibercrete mix developed by CNC in collaboration with Hansen Construction Materials exhibits high flexibility, toughness, and binding capacity. Its rheological properties allow it to be dropped via borehole from surface batching plants to depths exceeding 250 meters without loss of structural integrity. Underground, the material is collected in kibbles and pumped at high velocity using a flame-proof, self-propelled shotcrete rig, ensuring reliable placement in development roadways. When applied to ribs, roofs, and opposing walls, Fibercrete distributes load pressures evenly, reducing coal fretting, rib unraveling, and roof deterioration. Applied at design thickness, it significantly reduces the need for secondary bolting and mesh, while improving roadway stability. The sealed membrane also limits gas migration by filling coal cleats and forming internal baffles, reducing gas emissions into the roadway environment. CNC has further enhanced safety through a remote-operated flame-proof shotcrete rig with an extendable 9-meter boom, allowing spraying under supported ground while keeping personnel clear of high-risk zones. Application thickness is verified using embedded depth indicators, providing immediate visual confirmation of compliance. Overall, fiber-reinforced shotcrete delivers a safer, more efficient, and cost-effective ground support solution for coal mines. It reduces manual handling, minimizes rework, improves gas control, and provides a durable, life-of-mine support system aligned with modern underground mining requirements. The track demolition at Romanhofplatz represents a large-scale, tightly coordinated infrastructure operation executed with high intensity and precision. In the first phase of the project, a total track length of approximately 480 meters was dismantled within a compressed weekend work window, demonstrating the capacity for rapid urban rail intervention under constrained conditions. The operation was carried out by around 110 specialized KIBAG personnel, deployed in shifts to maintain continuous progress and strict safety control. Heavy equipment formed the backbone of the demolition works. Two large excavators led the primary braking operations, supported by 8-wheeled excavators, with operating weights between 10 and 22 tons, enabling flexible maneuvering in the dense urban environment. In parallel, 8 crawler excavators handled deeper structural demolition and excavation tasks. The removal of the road surface resulted in approximately 300 tons of asphalt material, followed by the demolition of roughly 700 cubic meters of concrete track structure. Material logistics played a critical role in maintaining workflow efficiency. A fleet of 44 trucks ensured uninterrupted transport of demolition debris and delivery of new materials. Around 900 cubic meters of excavated material were removed from the site, while an equivalent volume of gravel was delivered to prepare the substructure for subsequent construction phases. 2 bulldozers equipped with 3D machine control systems were used to achieve precise grading and layer thickness, ensuring compliance with design tolerances. Beyond track removal, the project incorporated essential underground infrastructure upgrades. New utility lines were installed, along with 16 sludge collectors and 14 cable chambers, integrating drainage and electrical systems into the rebuilt corridor. This first demolition phase at Romerhofplatz laid the technical foundation for follow-up railworks, with subsequent demolition stages scheduled in Bern and Zurich to continue the systematic renewal of urban rail infrastructure. The Gomaco GP3 is engineered as one of the most advanced and intelligent concrete pavers in the world, designed for paving widths of up to 30 feet with exceptional accuracy and control. At the core of the machine is the proprietary Gomaco G+ control system, which integrates all major paving, steering, and frame functions into a unified, intelligent platform. The GP3 features 14 feet of hydraulic frame widening using a dual telescoping frame equipped with industry-first smart cylinders. These cylinders provide continuous width reference data to the G+ controller, eliminating the need for manual measurement and enabling automatic steering setup and individual track speed control. A unique roller frame design builds camber into the frame as it extends, maintaining structural stability and paving precision. Intelligent leg positioning is achieved through sensored rotational drives on the leg pivots, allowing precise hydraulic rotation and automatic directional control of the tracks. Track steering is also sensored, ensuring continuous reference to the straight-ahead position while enabling extreme steering angles for tight maneuvering. Counter-rotation and transverse modes allow the paver to turn within its own footprint or move laterally with tracks automatically positioned at 90 degrees. Load-sensed hydraulics optimize performance and fuel efficiency, while G+ quiet technology reduces operational noise. The low-profile design, vibration-isolated operator platform, telescoping safety rails, and comprehensive safety systems enhance visibility, comfort, and job site safety. A high-rise concrete pour in Seattle requires carefully planned logistics, especially when transporting materials and fresh concrete to the 20th floor of an active construction site. On pour day, the concrete pour crew operates in tightly coordinated phases to maintain continuous placement and consistent quality across the elevated slab. Concrete is delivered at ground level, and pumped vertically using high-pressure concrete pumps designed to maintain flow stability over long vertical distances. Hoses and placing booms distribute the concrete evenly across the deck, allowing the crew to respond quickly as placement progresses around the slab. Clear communication between pump operators and deck crews is essential to avoid cold joints and ensure uniform coverage. Once concrete reaches the work area, crew members immediately begin spreading and leveling the fresh material. Shovels, rakes, and come-along tools are used to distribute the concrete, while screed bars and straight edges establish the correct elevation and slab flatness. This initial leveling phase is critical for structural accuracy and load performance. Internal vibrators may be used to consolidate the concrete, eliminating air pockets and ensuring proper bonding around reinforcement and embedded components. The pour continues methodically around the slab, maintaining a steady pace to control setting time. Environmental factors such as wind, temperature, and sun exposure at elevation are continuously monitored as they directly affect workability and finishing windows. Approximately 4 hours after placement, depending on mixed design and site conditions, the slab reaches the optimal state for finishing operations. At this stage, crews transition to surface finishing. Power trowels and hand tools are used to refine the concrete surface, increasing density and achieving the specified smoothness and flatness. Edges and tighter areas are finished manually to maintain consistent quality across the entire deck. Timing during this phase is critical. Finishing too early or too late can compromise surface performance and durability. Throughout the operation, strict safety procedures are enforced. Fall protection systems, controlled access zones, and equipment coordination are vital when working at the 20th floor. A successful high-rise concrete pour reflects disciplined teamwork, precise execution, and technical expertise, resulting in a durable structural slab ready for the next stages of construction. The ore and precast twin wall installation follows a controlled, step-by-step construction sequence designed to ensure safety, accuracy, and structural integrity throughout the erection process. Bean bags are placed along the trailer edges to provide effective fall protection for personnel during panel handling. Surveyors then set out the grid lines and install leveling shims to achieve precise alignment in accordance with the design drawings. Under the guidance of a banksman, lifting chains are securely connected to the designated lifting points on the twin wall panel. Once checks are complete, the banksman exits the trailer and signals the crane operator to proceed with the lift. The panel is carefully lowered into position, with a nail bar used to control final placement and prevent edge damage. Side alignment is adjusted using shims, while a consistent 10 mm vertical joint is formed between adjacent panels. Fine positioning, including a 400 mm offset where required, is achieved using crowbars and verified with a spirit level. Push-pull props are then fixed to the panel and anchored into the ground. The first prop is adjusted to align the panel with the existing wall, while the second prop is set in the opposite direction and locked to prevent movement. Sight tie steel is installed, the wall base is shuttered, corner brackets are secured, and concrete is poured into the twin wall cavity to complete the assembly. The Emedu single panel forms the structural core of the Emedu advanced building system, delivering a highly rationalized construction method based on load distribution, reduced weight, and integrated reinforcement. From the foundation stage, the technical advantages are evident. Regardless of whether strip footings, curbs, beams, or slabs are used, foundation dimensions can be reduced due to the uniform transfer of loads generated by the panel system. This directly translates into material savings and lower construction costs. Vertical starter rebars, typically 30 to 40 centimeters high with a 6 mm diameter, are cast into the foundation to anchor the structural panels. Panel installation then proceeds with precise positioning, alignment, and plumbing at ground level. Adjustable metal supports, aluminum bars, or conventional site materials such as timber braces are used to maintain accuracy during assembly. Panels are mechanically tied to each other and to the foundation rebars, ensuring full static continuity throughout the structure. Critical zones such as corners, joints, and highly stressed areas are reinforced with additional galvanized, electro-welded steel mesh. Where seismic performance or specific structural requirements demand it, supplementary internal reinforcement can be added without altering the system logic. Floor slabs, balconies, and cantilevered elements are easily integrated, thanks to the lightweight nature and handling efficiency of the panels, resulting in faster installation and improved structural homogeneity. Staircase panels are supplied ready for cladding and are anchored to pre-installed or subsequently added reinforcement bars. Electrical, plumbing, and mechanical services are installed by creating chases using hot air, eliminating demolition work. Final structural completion is achieved through internal and external shotcrete application, embedding the mesh and forming a monolithic, continuous load-bearing shell ready for architectural finishes. The Record Holtzman Easy-Click Foundation Formwork system is designed to simplify and accelerate the construction of concrete foundations, while ensuring high-dimensional accuracy and thermal performance. This video demonstrates the complete installation process, highlighting how efficiently the system can be assembled and prepared for concreting. Installation begins by placing the Easy-Click formwork directly into the excavated foundation trench on top of the blinding or cleanliness layer. The elements are lightweight, precisely manufactured, and engineered for fast on-site handling. Individual panels are simply joined together using an integrated tongue-and-groove or plug-in connector system, allowing quick alignment without complex tools or additional bracing. This mechanical interlocking ensures stable connections and accurate geometry throughout the foundation layout. To further improve tightness and prevent concrete leakage, all joints are sealed with standard assembly foam. This step enhances formwork stability and ensures clean concrete edges after pouring. The thermo version integrates insulation directly into the formwork, contributing to reduced thermal bridging and improved energy efficiency of the finished structure. The system supports a wide range of foundation configurations. Corner elements are easily formed using standard components, while precise cutouts can be created for drainage pipes, service ducts, and other penetrations. This flexibility allows the formwork to adapt to real construction conditions without compromising speed or accuracy. The Easy-Click system significantly reduces installation time, labor effort, and potential errors compared to traditional timber formwork. By combining fast assembly, thermal performance, and permanent formwork functionality, Rickard Holtzman delivers a modern solution that allows construction teams to move quickly from formwork installation to concreting, efficient, precise, and reliable. Once fully assembled and secured, the foundation formwork is immediately ready for concreting. Concrete is poured directly into the formwork, which remains in place after curing, eliminating the need for stripping and reducing labor time. The result is a clean, dimensionally stable foundation with integrated insulation and smooth concrete surfaces. China's high-speed railway network continues to expand rapidly, supported by large-scale engineering, advanced mechanization, and standardized construction methods. In North China's Shanxi province, construction is underway on the Detong-Zhangjiakou high-speed railway, a 140-kilometer line designed for operating speeds of up to 250 kilometers per hour. Once completed, travel time between the two cities will be reduced to approximately 40 minutes, with direct connections to Beijing taking around 100 minutes, a significant improvement over conventional rail travel. Construction of the line began in November 2015 and has progressed steadily toward commissioning. The project plays a strategic role in regional connectivity and is an important transport corridor, supporting the Beijing-Zhangjiakou area, one of the host regions for the 2022 Winter Olympics. The railway is designed to meet modern high-speed standards, emphasizing safety, ride comfort, structural durability, and operational efficiency. At the core of track construction is a highly automated rail laying system developed by China Railway Construction Corporation. This specialized rail laying machine operates as an integrated unit composed of three main sections. The front section functions as a rail pulling system, capable of handling 500-meter-long welded rails. The central power and control unit provides traction and synchronization for the entire system, while the rear transport section consists of multiple flatbed cars that carry steel rails, concrete sleepers, and fastening components. Together, these elements form a mobile logistics platform that supports continuous track installation. Long welded rails used in the project are produced by joining multiple 100-meter rails at dedicated welding plants using seamless welding technology. The resulting 500-meter rails are transported to the construction site on specialized rail transport systems and fed directly into the laying machine. This approach minimizes joints, improves track smoothness, and reduces long-term maintenance requirements. The railway adopts a ballastless track structure, which is standard for high-speed lines. Instead of traditional ballast, reinforced concrete track slabs are used to provide higher stability, improved geometric accuracy, and lower maintenance demands. This slab-track system offers superior performance under high-speed and high-frequency train operations, while also reducing lifecycle costs. During installation, concrete sleepers are precisely positioned by automated handling arms integrated into the rail laying machine. Mechanical positioning systems ensure millimeter-level accuracy in sleeper alignment. Steel rails are then placed onto the sleepers, fastened and secured using high-strength fasteners. The level of automation significantly reduces manual labor while increasing installation speed. With this mechanized approach, only a small team of technicians is required. Yet more than 2 to 3 kilometers of track can be laid per day, compared to roughly 500 meters using traditional manual methods. After track laying, additional engineering processes are required before the line can enter service. These include fine adjustment of track geometry, stress release and locking to compensate for thermal expansion of steel rails, and precision track alignment to ensure smooth vehicle dynamics. Comprehensive inspection procedures follow, including static and dynamic testing, to verify safety, comfort, and structural integrity under operational conditions. Power supply for China's high-speed railways is provided by dedicated substations, supporting reliable traction energy delivery. The network is designed to support maximum commercial operating speeds of up to 350 kilometers per hour on selected corridors. By the end of 2017, China's high-speed rail network had reached approximately 25,000 kilometers, accounting for more than 60% of the world's total high-speed rail mileage, with no major safety accidents recorded. Continued investment remains substantial, with thousands of kilometers of new lines added annually. The Datong-Zhangjiakou line represents a small but essential component of a national grid structured around east-west and north-south corridors. Advanced construction equipment, digital control systems, and standardized engineering practices have transformed high-speed railway construction into a highly efficient, industrialized process. Through mechanization, automation, and strict engineering standards, China's high-speed railway projects demonstrate how modern infrastructure can be delivered at scale while maintaining high levels of safety, precision, and operational performance. Preparing and paving with asphalt is a highly structured construction process that relies on precise sequencing, specialized machinery, and strict quality control to achieve a durable, smooth pavement surface. Each phase plays a critical role in ensuring long-term performance under traffic loads and environmental exposure. The process typically begins with surface preparation using a Wirtgen W200 cold milling machine. This high-capacity milling unit removes the existing asphalt layer to a controlled depth, eliminating surface distress, such as cracking, rutting, and oxidation. The W200 uses a rotating milling drum equipped with tungsten carbide cutting tools to grind the pavement accurately while maintaining a consistent profile. Integrated conveyor systems transfer the milled material directly into haul trucks, keeping the work zone clean and efficient. Milling also restores proper elevations and cross slopes, which is essential for drainage and final ride quality. Before paving, a rock spreader is used to place a uniform layer of aggregate where required. This step is particularly important in areas needing additional structural support or improved load distribution. The rock spreader ensures consistent thickness and even distribution, which contributes to pavement stability and prevents weak spots from forming beneath the asphalt layer. Next, a tar coat, commonly referred to as a tack coat or prime coat depending on application, is applied. This asphalt emulsion is sprayed evenly across the prepared surface to promote adhesion between layers. Immediately after application, gravel may be spread over the tar coat to enhance bonding and provide a stable working surface. This composite layer helps lock the structure together, reducing the risk of slippage, delamination, or premature failure under traffic. Once the tar and gravel layer has set appropriately, sealing and leveling operations begin. A specialized sealer or leveling course is applied to correct minor surface irregularities and ensure uniform thickness before final paving. This step flattens the surface, fills shallow depressions, and improves overall smoothness. Precision during this phase is essential, as any imperfections left uncorrected will transfer to the finished pavement. With the base fully prepared, it is time to pave. Asphalt pavers receive hot mix from delivery trucks and place it in a continuous, uniform mat. The paver's screed is the key component controlling thickness, width, and surface texture. Modern pavers use automated grade and slope controls to maintain design specifications with high accuracy. Consistent feed to the screed is critical to prevent surface tearing or uneven compaction. Edgework and joint construction are treated with particular care. Longitudinal and transverse joints are compacted thoroughly to prevent weak seams. Hand tools are often used along edges, around structures, and in confined areas to maintain consistent quality where machines cannot operate effectively. Immediately behind the paver, compaction operations begin. Steel drum rollers and pneumatic tire rollers compact the asphalt while it is still within the optimal temperature range. Compaction is performed in multiple passes and patterns to achieve target density, reduce air voids, and increase load-bearing capacity. Proper compaction is one of the most important factors in pavement longevity, directly influencing resistance to water intrusion, deformation, and cracking. Temperature management is closely monitored throughout paving and compaction. Asphalt that cools too quickly cannot be compacted effectively, while overheating can damage the binder. Crews coordinate closely to maintain a steady workflow, adjusting roller patterns and timing based on ambient conditions, wind, and asphalt mix design. After compaction, the pavement is inspected for smoothness, thickness, and overall finish. Any minor surface defects are corrected immediately while the asphalt is still workable. Once the surface has cooled sufficiently, the pavement is open to traffic or prepared for additional layers, markings, or sealing treatments as required by the project specifications. To support coastal protection and disaster mitigation, wave-dissipating concrete blocks play a critical role in reducing wave energy and preventing shoreline erosion. The manufacturing process of wave-dissipating concrete blocks. The production workflow is divided into 4 main stages: formwork assembly, concrete placement, demolding and repositioning, and concrete curing. The process begins with large formwork assembly. The sequence follows the installation of the main form panels, end plates, and finally, the working scaffolding. Formwork components are lifted and positioned using a crane to ensure accuracy and safety. Pre-assembled formwork sections are connected using taper pins, cotter pins, and locking counters to achieve a rigid and precise mold. Once assembled, a release agent is sprayed on the inner surfaces to facilitate clean demolding after curing. Concrete placement starts with ready-mix concrete delivered by truck agitators, which discharge into a concrete pump truck. The pump transfers concrete directly into the formwork through a delivery hose. Even during rainy conditions, protective sheet systems prevent rainwater contamination. Prior to placement, on-site quality control tests are conducted, including slump, air content, concrete temperature, and unit water content. Test specimens are prepared for later compressive strength testing. Concrete is placed progressively from the bottom upward. Due to the tetrapod's height of approximately 4 meters, access ladders and safety harnesses are mandatory. Internal vibrators are applied at each leg of the tetrapod to ensure proper compaction and eliminate voids. Upper layers are cast in the same manner, and excess latence is removed after placement. Before finishing the top surface, a specialized tool is used to remove surface air bubbles, significantly improving surface quality. After final finishing, a curing compound is applied. Once initial curing is complete, the formwork is removed, cleaned, and prepared for reuse. The tetrapod then undergoes membrane curing, where a curing agent is applied to prevent moisture loss. This completes the production of a durable, high-quality wave-dissipating block. The New Holland RG140.B motor grader is a robust and precise machine designed for grading, spreading, and surface preparation in road construction and industrial applications. In this operation, the grader is used to spread slag material with a controlled thickness of 10 centimeters, demonstrating both the machine's accuracy and the operator's technical skill. Equipped with a powerful engine and a well-balanced chassis, the RG140.B delivers stable performance even when handling dense and abrasive materials such as steel slag. The moldboard, mounted on a reinforced circle and drawbar system, allows fine adjustment of angle, tilt, and pitch. This flexibility is essential for achieving uniform layer thickness and consistent material distribution across the working surface. During the operation, the operator carefully controls blade height and angle to ensure the slag is evenly spread without segregation. Hydraulic responsiveness enables smooth blade movements, maintaining a constant 10 centimeters layer while minimizing material displacement outside the design profile. The articulated frame improves maneuverability, allowing precise alignment and smooth transitions, especially on long passes. The RG140.B's operator station is designed for visibility and control. Clear sightlines to the moldboard and working area support accurate grading, while ergonomic controls reduce fatigue during extended shifts. This is particularly important when working with granular or irregular materials that require continuous monitoring and fine corrections. From a technical perspective, the spreading of slag at a uniform thickness contributes to proper load distribution, surface stability, and long-term performance of the base layer. Consistent compaction and leveling at this stage are critical for subsequent construction layers.
In Egypt, sugarcane waste is often illegally dumped or burned, releasing harmful carbon dioxide. Researchers have found a way to incorporate sugarcane bagasse ash into concrete to reduce environmental impact. By collecting, drying, grinding, and carefully burning the waste in low-oxygen conditions, they produce ash that replaces up to 10% of Portland cement. Tests show strength remains adequate, making this a sustainable alternative.